Yeah, good morning, students. Welcome back. Yeah, we'll again start with the recapitulation of what we have discussed in the yesterday's class. Specifically, many of you are expressing a doubt on the how the energy band, that is valence band and conduction band, has been formed. Okay, when you form the crystal structure. Okay, so briefly I'll explain. Please concentrate. Okay, please try to understand this. See here, we have started with the isolated, silicon atom. Okay. Now, when it is isolated, the energy levels that we can represent are going to be discrete. Okay. So here for 1s orbit, there are two energy states that are going to be available at the same energy. Okay. And it can be occupied by two electrons. And p orbital is going to have 6 energy levels. Okay, 6 states. Okay, or energy states or energy levels. Okay, and 6 electrons can be occupied. Okay, hope I am clear. Now, for our silicon atom, if you write the electronic configuration, it is 1s2, 2s2, 2p6, 3s2, 3p2. So you can very clearly see the outermost orbit is having the 4 electrons, valence electrons. Okay, so this is what we have represented. Okay, so here this is the 1s orbit where I have two available states. Circle indicates what? Available state. And if I put a cross mark, this is our notation. Okay, for our understanding purpose I am putting. So I am putting a cross mark which indicates it is occupied. Okay, so in the 1s we have 1s2 here, so both are occupied. 2s also both are occupied. 2p, all the 6 states are occupied. 3s, both the states are occupied, but 3p, it is 3p2 only. Available states are 6, but the occupied states are going to be only 2. This is when you take it as an isolated atom, single atom. And then we have seen n isolated atoms. Okay, so still there is no interaction between the atoms, still they are isolated. So I have 2n states now, yes or no? One s orbital is going to have 2n states. Each is having 2 states. There are n atoms, so 2n states obviously. And for p orbit, each is having 6 states. Now for n atoms, n isolated atoms, it is 6n. Okay, hope I am clear. So based on that, we have written this. Please here try to understand. Okay, see, already crystal structure has been formed. Okay, you are not reducing the interatomic distance and forming. Naturally it was formed, but for our understanding purpose we are using that, to make you to understand. I'm giving that. Okay, now what you are doing now, the x-axis is going to be the atomic distance. Okay, and the y-axis is always what? Electron energy. Okay, now you start bringing these atoms close to form the crystal structure. What will happen? The outermost electrons are the outermost, okay, orbits, the electrons which are present in the outermost orbit, they are going to start interacting with each other. And according to the Pauli's exclusion principle, no two electrons, okay, is not going to have same energy. Because of that, what will happen now? You can see very clearly here. If you consider 6n states here for 3p, okay, till to this point, okay, all the 6n electron volts are going to have the same energy. 6n states or 6n electrons are going to have the same energy. I'm talking Pauli's exclusion principle come into picture when you are talking as a system. Please keep it in mind. Okay, when you call it as a system, then you have to apply that. Okay, but these things are going to be initially isolated. No, you cannot call them as the system. Okay, now when you bring them and form a crystal structure, now it is a system as a whole. Then you have to apply the Pauli's exclusion principle. Okay, so from this point onwards, okay, so it is forming a system now slowly. Okay, so what will happen? 6n states are having at the same energy, no, 6n, all the 6 G. Okay, but now what will happen? 6n states will be there. Okay, but each state, okay, there will be a little bit amount of difference, energy difference. Okay, very small. We'll see in the numerical example also. There will be a small difference. Okay, so that what will happen is it is going to split here. Let me indicate here. It's going to split. Now it's going to split like this with a very difference. Like this it is going to split. Okay, so each horizontal line represents one energy level. Like this it is going to split. Okay, and that is what we have taken. And as you are keep on decreasing the interatomic distance, okay, so this type of structure you are going to get. Okay, so here this is what we are taking as the valence band. No, so we can have, we can represent something like this here, like this. Okay, so here this is the conduction band. Okay, so these energy levels, discrete energy levels, now forming a band. Please understand it. It is forming a band. Okay, and here also you will have the same similar type of thing. Okay, so this is how the energy band is going to form. Okay, and here, depending upon the interatomic distance, okay, you can see from this point onwards, what is happening? The energy, whatever the energy levels that I have here continuously, they are split into two bands. One is called as the valence band, the other one is called as the conduction band, separated by energy gap. And within the energy gap, okay, there are no energy levels that are allowed, and no electron can present within this energy gap. And that is the reason why we call it as what? Forbidden band. This energy gap is also called as what? Forbidden band. The name itself is indicating. Okay, so this is how actually the valence band and conduction band is formed. And we know very clearly that the electrons are going to occupy the lowest energy levels that are possible first, and then they will go for the higher energy levels. Because of that, you can see very clearly valence band is completely filled and conduction band is completely empty. Okay, yes. So here the three basic principles we have discussed. Okay, so what are the three basic principles of energy band diagram? The first one is the allowed states. That is what I have again explained. Now, not only that, we need to understand how these energy levels are distributed. That you must understand. Okay, and then out of which how many are occupied. That is what we have we are trying to discuss. Okay, and anyhow, this is the representation of the energy band diagram and the correspondence. And here, to understand this distribution of the states, allowed states over the energy here, okay, in either conduction band or valence band, you need to have some mathematical representation. Okay, but with single equation, we are not in a position to describe the entire variation within the conduction band and within the valence band. For that, we are taking the parabolic approximation. Okay, and you can represent like this. And another important principle, the third principle is what? Fraction of the occupied states at any given energy level E and a given temperature T. Okay, so this is based on what? Fermi-Dirac distribution function. Okay, this is nothing but what? Fermi-Dirac distribution function or Fermi-Dirac probability function. Okay, so this is how it is given. Okay, and mathematically we have seen what it is, and what physically it is going to represent also we have discussed. Okay, yes, and as you are increasing the temperature, what will happen? Some of the electrons can move from valence band to conduction band. Okay, so what will happen? At absolute zero, we have drawn this one, the green dashed line which I have represented. This is for corresponding to what? T equal to 0. As you are increasing the temperature, this will become slightly more than 0. Here it is slightly less than 1. Okay, so like that we have represented, or we have given this variation of the Fermi level. Okay, hope I am clear. And we have given the physical significance. What is the physical significance? Now if we consider at absolute zero, all the energy levels which are present below the Fermi energy level, they are filled. Nothing but you can see even the energy band diagram that we have given, no, this one. You have Fermi energy level. Actually within the energy gap, you can represent the Fermi energy level. Now this band is the valence band, which is present below the Fermi energy level. All are filled, and above they are empty. Okay, so this is at absolute zero. Okay, and if you make T greater than 0, and if I put T is greater than 0 and E equal to EF, you can get very easily F of E comma T equal to 0.5. What is the meaning of that? half of the available states are going to be occupied. Okay. Yes. And we have given one approximation called as Boltzmann approximation. And we have given the condition is what? E minus EF should be greater than or equal to 3 kT. Okay. Even you can put the equality also here. Okay. And here it is E minus EF less than or equal to minus 3 kT. Then you can apply this. Okay. We have seen how we can simplify the thing. Okay. And we have given what is the physical difference between Fermi-Dirac distribution and the okay, derivation and the Boltzmann's approximation. Okay, yeah. Let us consider a numerical problem here. Okay, so that we can understand some of the concepts in a better way. Okay, now I'm consider an electron which is traveling at a velocity of how much? 10 power 7. Okay, 10 power 7 centimeters per second. Okay, and assume that the velocity increases by a value of 1 centimeter per second, and we need to calculate the change in kinetic energy of the electron. Okay, yes. Now we know very well what is the kinetic energy. Yes, what is the kinetic energy? Let me write. What is kinetic energy? Half mv square. Okay, now let us consider it is moving with a velocity v1, then the corresponding energy I can write it as E1. Okay, so let us take this is E, and a velocity of v2 corresponding to that I can have an energy of E2. Okay, yes. Now can I say delta E? Okay, and anyhow it is increasing, so we can very clearly see that v2 greater than v1. No, he has mentioned very clearly that it is increasing. Okay, so v2 is greater than v1. So now can I say change in kinetic energy delta E is nothing but what? E2 minus E1. So which is equal to half m into v2 square minus s. Okay, now what is v2 actually? Now let us take v2 is nothing but v1 plus delta v. Am I correct? V1 is the initial and there is a change. Delta V is the change. Okay, then what is V2 square? I can say V2 square is equal to V1 plus delta V whole square. So which is V1 square plus 2V1 delta V, okay, plus delta V whole square. Yes, okay. Now put this V2 into this equation, okay, and find out what is delta E now. Now delta E is equal to half into m into, okay, so you can very clearly see this is your, yeah, 1 second. Before going to that, we can have some approximation here, okay. So V2 square is equal to, you can very clearly see delta V, okay, whatever delta V is there, this is going to be much less than V1, because V1 is this one, no, 10 power 7 centimeters per second, and this is the delta V. You can very clearly see compared to V1, delta V is going to be very small. So what I can say, can I say V2 square approximately equal to V1 square plus 2V1 delta V. Okay, so this term delta V square term I am neglecting compared to V1. Okay, so it's a by relatively I am ignoring it. Okay, now let us write what is delta E now. Let us write what is delta E. It is half m into, now put this V2 square into this equation. Okay, so you can V1 square and V1 square will get cancelled. Okay, so what I'm going to get, it is 2 times of V1 into delta V. So 2 also gets cancelled. So what I'm going to get, delta E is equal to, it is m into V1 into delta V. Okay, yeah, please don't try to remember this equation, try to sorry, understand how we are getting it. Okay, now you just substitute the values. So delta E is equal to, what is the mass of electron? So here, if it has not mentioned mentioned about the mass, you can take the actual mass. So what is it? It is 9.1 or 9.11 into 10 power minus 31 kgs. Okay. If that is the case, what should be V1? I should write. Please again, I'm giving a a warning to you. When you are substituting the numericals, you need to be very careful. Okay. So what are the units that I have written here? 9. I'm sorry, 9.11 into 10 power minus 31 kgs. Then the velocity I should write in meters per second. So then it should be what? 10 power 5. It is not 10 power 7, please. 10 power 5 meters per second. But given is 10 power 7 centimeters per second. That is why I am writing 10 power 5. Okay. Hope I am clear. Into. What about this? 1 centimeter means 10 power minus 2 meters. So it is 0.0. Be careful. See, if it is a objective type question, okay, you will have option A as whatever 9.11 into 10 power minus 31 into 10 power 7 into 1. Whatever the answer that you are going to get, that will be there. Okay, so be careful. Okay, so you calculate this. Okay, this will give 5.7, sorry, 9.11 into, okay, anyhow, this is 10 power minus 2. Okay, this is 10 power 5. Okay, you can cancel 10 power minus 28. What are the units I have to write for the energy now? Is it joules or electron volts? Please, whether I have to write joules or electron volts, it is joules. Because I am taking here kg, no, it should be joule here. Okay. Now we know 1 electron volt is equal to how much? 1 electron volt. 1.6 into 10 power minus 19 joule. So based on that you convert. Okay. So this value will give delta E is equal to 5.7. Okay. Into 10 power minus 9 electron volts. So this is the answer that I am going to get finally. 5.7 into 10 power minus 9 electron volts. Okay, hope I am clear. Yes, so simple mathematics I have used. Okay, so finally this is what you are going to get. Again, I am giving many times I'm saying this. Be careful with the units or dimensions that you are going to substitute numerical values. Okay, so there is a very possibility that even though you know the correct formula, when you are substituting, you can put it in wrong way and you may get the wrong answer. Okay, so in the competitive exam, the examiner will have mindset in such a way that, okay, he will try to eliminate as many students as possible. Okay, not only with the subject, he will test in all the directions. Okay, so it is very important one. Okay, fine. Now what? Okay, mathematically it's okay. Okay, but what this physically it is going to represent? If you see the change in the velocity, what is it? 1 centimeter per second. Okay, what is the change in energy? It is 5.7 into 10 power minus 9 electron volts. Now, if you see the 1 electron volt here, whatever we have written earlier, okay, this 1 electron volt, it is in the order of 10 power minus 19. But if you compare delta E and 1 electron volt, which is the larger value here? Delta 10 orders of magnitude is larger than your 1 electron volt. But in this case, for only 1 centimeter per second variation, you can see very clearly there is a large variation in the energy. Large variation in the energy. Okay. Compared to what? That is important here. Please concentrate. Compared to what? 1 electron volt. I am talking. Hope I am clear. The reference what I am taking here is 1 electron volt is 1.6 into 10 power minus 19 joules, because this is the electron energy that we are going to represent in the energy band diagram. Okay. So compared to this 1 electron volt, we can very clearly see that delta E is 5.7 into 10 power minus 9. Okay. This is 10 power minus 9, please. Okay. 10 power minus 9 electron volts. So 10 orders of magnitude larger value, but actually 1 centimeter per second when compared to 10 power 7 centimeters per second is going to be very small value. So here you can see for small variation in the velocity, there is a large variation in the energy. So what you can understand from this is, if you see the that energy band diagram that we have drawn. Okay, let me indicate for the outermost shells. We have represented like this something. Yes, and here we have given something like this. Yes, and like this we got. Okay, so it's nothing but for very small variation, no, so the energy levels are going to be distributed, okay, very close to each other, so that we can call it as quasi continuous. Whatever the energy levels that I'm getting, what it is, quasi continuous. So we have given what is meant by quasi. There is a small, so actually these energy levels should be continuous, but you can see from this numerical example it's going to be what, quasi continuous. Okay, so please try to spend some amount of time to understand this one. See, whatever mathematical or numerical things that we are giving, you try to interpret physically so that you can better understand the concept. Okay, hope I am clear. Now let us go for the next problem. Okay, so what is let me read the question. Let T is equal to 300 Kelvin. We are considering at room temperature. Determine the probability that an energy level, okay, energy level 3 kT above the Fermi energy is occupied by an electron. Okay, so energy level 3 kT above the Fermi. What is the meaning of this? Can I say E minus EF is equal to 3 kT? Am I correct? Yes or no? Okay, and we know what is the formula for probability of finding the probability that a particular energy level is occupied. What it is? F of E comma T is equal to 1 over 1 plus E power E minus EF divided by KT. Okay, so this is equal to what? 1 divided by 1 plus E power E minus EF is what? 3 KT divided by KT. Okay, so you calculate this value, you will get it as 0.0474. What it is? 0.0474. Okay, so you can very clearly see what is the probability. You can see the probability value. Okay, so what you can conclude from this one, the energy levels which are present above the Fermi energy level, the probability of occupying those energy levels is going to be very, very less. Am I clear? That is what we have taken. The E which we are considering here is above the Fermi energy level by 3 kT. So we can very clearly understand from this that the probability that a particular energy state above the Fermi energy level, okay, is going to be occupied by the electron is going to be very small value. Okay, hope I am clear. Now let us go for next one. Okay, see the next problem. So assume that the Fermi energy level for a particular material is, okay, it is given. EF is given. Okay, so what is this value? 6.25 sorry, electron volts. Okay, and that the electrons in this material Dirac distribution function, that is f of E comma T, you can write. Calculate the temperature at which, okay, there is a 1% probability that a state 0.3 electron volts below the Fermi energy level will not contain an electron. Okay, hope I am clear with the question. Yes. Okay, so what is the probability that a particular state is occupied? F of E comma T. Okay, let me write that. Probability that an energy level is occupied, okay, or filled. What is that? It is F of E comma T 1 over 1 plus E power E minus EF divided by KT. So what is the meaning of this F of E comma T? Why I am putting F of E comma T? It is a function of energy where we are considering also temperature. That is the reason why you are writing F of E comma T. Is it fine? Okay. Now, if that is the case, what is the probability that a particular energy level is empty, is or unoccupied? It should be 1 minus f of e comma t. Okay. So can I say probability that an energy level is unoccupied, okay, or empty? So what it is? It is, let me write here, it is 1 minus f of e comma t. Okay, so is nothing but what, which is equal to 1 minus 1 over 1 plus e power e minus ef divided by kt. Am I correct? Yes. Now this is given. Okay, your left hand side in the problem they have very clearly mentioned it is 1%. Okay, you can read the question. Calculate the temperature at which there is a 1% probability that a state 0.3 electron volts below the Fermi energy level will not contain an electron. Okay, so can I say 1 minus f of e comma t is 1%, means 0.01 sorry, is equal to 1 minus 1 divided by 1 plus, okay, e power. What is e minus ef is going to be here? What is e power? Sorry, e minus ef is going to be where the energy level you are considering. It is below the Fermi energy level. How much? 0.3 electron volts. Means what? E minus ef is minus 0.3. So simply I can say it is minus 0.3 divided by kT. Okay. So you can get kT from this. Please calculate. Okay. You will get kT is equal to 0.06529 electron volts. Okay. And you know the value of K. Okay. Boltzmann constant that you can substitute. So K is equal to 8.62 into 10 power minus 5. Okay, because here expressing in electron volts, I am writing in electron volts here. Otherwise it is in joules, you can use other value. Okay, 1 electron volt is 1.6 into 10 power minus 19 joules, you can put, you will get the other value. Okay, so you calculate the value of T here, you will get T is equal to 757 Kelvin. Okay, finally you will get the temperature value is how much? 757 Kelvin. Okay, hope I am clear. Yes. So whatever, you know, earlier we have taken the mathematical expressions. Based on that we are doing the problem, numerical problem, so that you can understand in a better way. Okay, so try to, you know, understand numerically what they are going to represent. Okay, hope I am clear. Yes. So so we have seen basically what now, for the intrinsic semiconductor material. Okay, we have discussed about the band model. Please, again I am repeating this point, whatever the band model that we have discussed now, in case of extrinsic semiconductor material, similar type of analysis we are going to do, only the thing with little modifications we have to do. Okay, so we'll see at that point of time what we can able to, okay, modify. Okay, now let us go for next, okay, topic that we need to consider. Now we need to overlap the three principles that we got now, starting with allowed states, okay, then how they are distributed, and out of which how many are occupied. If I know that, I can calculate how many number of electrons are going to be present in the conduction band and how many number of holes are in the band. Okay, so please, if I say electron, please remember, okay, default we are talking about, you know, electron in the conduction band. Specifically if they talk, that is a different issue. It can be in the valence band also. Okay, and if I talk about the holes, where they are going to be present, holes, whatever the reference that we have given, it is in the valence band. Please keep it in mind. Okay, please keep it in mind. Holes, they are going to be present in the valence band. Electrons, nothing but free electrons, they are going to be present in the conduction band. Even though if I am not mentioning default, okay, in many textbooks they will not mention it is in corresponding bands are going to be that. Electron is in conduction band. Okay, electron means what? Free electron. Please keep it in mind. Okay, hole, valence band. Okay, now let us consider. We'll try to find out concentration of electrons in the conduction band. Okay, so let me write that. Concentration of electrons in the conduction band. Okay, yeah, here again we'll go step by step. Okay, and we are not going to go for too much mathematical derivations and all, but we must understand some few physical phenomenon and physical things. Okay, that is important. My concentration is going to be on that. Okay, please keep it in mind. Okay, yeah, now let us take, this is the, okay, I'm taking, this is the electron energy. Fine. Okay, let us take, this is top of the what, conduction band, and this is, let us take EC, which is bottom of the conduction band. Let us take, this is EC. Okay, and this is bottom of the conduction band. This is top of the valence band, EV. Okay, and this is bottom of the valence band, EB. Hope I am clear. Okay, the four energy states that we have, I am representing. Okay, and anyhow, this is the energy gap. You know this. This is the energy gap. Okay, now let us indicate. So these are the allowed state. The first information I have represented in the energy band diagram. What is that? Allowed states. Now let us go for next one. What is the next one? What is the next one? Distribution of allowed states. Okay, so anyhow, our interest is in the conduction band. Let us not too much concentration on the valence band. I am concentrating on the conduction band. Okay, now let us take, this is, what is this? This is going to be your N of E, distribution of allowed states. Hope I am clear. Okay, then what is the next information that we need to represent here? Fraction of occupied states. How, with what you are going to represent this fraction of occupied states? Fermi-Dirac distribution function f of E comma T. And I'm sorry, when we are discussing about the Fermi-Dirac distribution function, I have given one important point that f of E comma T is going to be symmetrical with respect to Fermi energy level EF. Okay. Now, right now, we don't know where exactly the Fermi energy level is going to be present. Okay. Anyhow, for intrinsic semiconductor, approximately at the middle of the energy gap, this Fermi energy level is going to be located. Anyhow, very soon, maybe within 20 minutes, we are going to see that. Okay. So for time being, you understand it. Okay. Yes. So the Fermi energy level semiconductor material is going to be located approximately at the middle of the energy gap. So based on that, okay, so I can draw, suppose if this is the middle of the energy gap, okay, this is the middle of the energy gap, then I can represent something like this now. Please try to understand. Okay, so what is this one? This is f of E comma T. Okay, am I clear? Yes. Yes. So the three informations I have represented within the energy band diagram. So this EF, EC, there is an energy gap, EV, EB. Okay. If you want, you can write this also. This is energy gap. Anyhow, this is not required, but anyhow, I am representing energy gap. Okay. So this is the information regarding the what? First one, allowed states. Second one, you need to represent the distribution of the allowed states, and then fraction of occupied states. Okay. Now what we are going to do is, now let us consider Okay, an energy interval within this, conduction band. Suppose if this is the energy interval that I'm going to consider. Okay, so I'm considering an energy interval of how much? dE. Okay, so what I'm going to do is, initially I'll find out how many number of electrons are present within this energy interval dE, and then you integrate throughout the conduction band, I can get the total concentration. Okay, I'll repeat this point. I'm considering an energy interval of dE in the conduction band. So what I'm going to do, first I'll find out how many number of electrons are present within this energy interval. Sorry. And then integrate over the conduction band, you can get the total. Yes, hope I am clear. So can I write like this now? Can I write like this? Because I have considered the differential energy level, the number of electrons that are going to be present are also differential. So Dn is equal to, okay, so what I can write? See, please try to concentrate. This is going to be very simple. Okay, if you know the mathematics, simple mathematics, you can easily understand. Okay, please let us concentrate. N of E represents what? This represents the total number of energy levels that are going to be present within the conduction band. But I have considered only energy interval dE. Am I correct? Only energy interval. Okay, dE. This one. I have considered only this. Now, how many number of states are going to be present within this? You observe this dashed line, dashed area is there, no? What is that? It is what it is. Total it is N of E, but I have considered only sorry, energy interval dE. So how many are present? N of E into dE. Okay. So these are nothing but what? Please try to concentrate again. N of E dE is the number of states that are going to be available within an energy interval dE. But Dn is nothing but what? Number of electrons means occupied states. Can I say? You just multiply with the probability. What is that? F of E comma T. Am I clear? Yes. Okay. Now, once if I know, this value, then you go for integration over the conduction band. That is what we can do now. Okay. Now, can you identify in this graph what we are given? No, where I can represent this Dn? Please try to understand. Please, I want this Dn to represent within this graph. Where I can able to represent? It should be what? Common to N of E, dE, F of E comma T. We can very clearly see N of E is this one, dE is this. So this, whatever the shaded area, no, that is going to be N of E into dE. And here, where I am getting F of E comma T, this is F of E comma T. Now, okay, I'll put one more cross mark here with the blue, okay, this area. So this is nothing but what? Dn. Am I correct? This is nothing but what? Dn. Okay. And if you want to calculate n, what you must do? You must integrate within the conduction band. So from EC to ET, N of E dE into F of E comma T. Hope I am clear with what I have written. Yes. Okay. Now please try to understand whatever I am going to draw now. Please. Suppose if I represent, so this is the EC, this is ET, okay. And what about this one? It is N of E, okay. Am I correct? And somewhere here, it is the middle of the energy gap, okay. And EI will be there at the middle of the energy gap. So what is F of E comma T? This one, okay. Anyhow, this F of E comma T. Now please tell me, I'll put a line here. What is this one is going to represent? Please tell me. Please, this blue line what I have drawn now, what it is going to represent is nothing but it is n of e into f of e comma t. Am I correct? Please try to understand. Whatever the blue line that I have given now is nothing but n of e into f of e comma t. And if you calculate area under this one, that will give what? N. Okay, let me draw that also. Okay, so this is n of e. Yeah, the similar type of discussion again we are going to make for concentration of holes in the valence band. Please try to understand. This is nothing but f of e comma t. Now, what I am going to do? I am going to calculate what is the area under this curve, this one. So this is nothing but what? N, and that is what we are going to calculate. So I have represented graphically here. We'll do mathematically what it is going to be. Hope I am clear. Yes. Okay. Now let us consider how to get n. This is the expression for n now. This one. We need to integrate within the conduction band. So let us consider that. Okay. Anyhow, here I am not going to do the integration and all, but we must understand some approximations. Okay. And finally, I'll give the equation. Okay. But that equation is going to be very important. Okay. And you need to understand what is the significance of each and every term which is going to be present. Okay. To answer the, please remember, answering the theoretical question is much more difficult than answering a numerical problem. Numerical problem, at least if you remember the formula, you can do something. For answering the theoretical question, you must understand the concept. Okay, so please try to concentrate. Now what we got, n is equal to, okay, we need to integrate, okay, where within the conduction band, EC to ET, n of e into dE into f of e comma t. Okay, so here we are going to make three approximations. We'll see one by one what the okay. Yeah. Now let us consider. Please concentrate. See here, this is the top of the conduction band. No, top of the conduction band. Now, if you see this, f of e comma t is becoming 0. Okay, well below your ET. You can very clearly see from this. Please try to understand. The top of the conduction band ET, which we are considering here, we can very clearly see this f of e comma t is becoming 0 well below the EF, well below the EF. So the position of ET will not affect your f of e comma t value now. Either it is present here, here or at infinity, it doesn't matter for f of e comma t. So for that reason, this is the first approximation that we are going to make. I am putting ET to infinity. So this is the first approximation. Am I clear? Okay. Please concentrate. The value of f of e comma t is becoming 0 well below ET. So the position of ET is not going to affect the value of f of e comma t. So that is the reason why I am putting at infinity. Okay. Yes. Now, anyhow, we know for the density of states function, what approximation we are using? Parabolic approximation. Parabolic approximation. Okay, nothing but what is this value? Some constant a1 into under root e minus ec. Yes. Then coming to the third approximation, okay, it is nothing but Boltzmann approximation. What it is? Boltzmann approximation. Okay, Boltzmann approximation, nothing but I can say fb of e comma t, you can write. Okay, so these are the three approximations that we are going to apply to find out the finally what is the value. Okay, So you here I'm not going for no differentiation and all, but you must understand these approximations how you are applying. Okay, and calculate the expression. I'm going to get n is equal to 2 times of 2 pi mn kt divided by h square whole power 3 by 2. Okay, into e power minus ec minus ef divided by kt. Okay, yes, or I can say simply n is equal to this entire term, will take it as nc here, nc e power minus ec minus ef divided by kt. Okay, okay, if you do the integration and all, finally we'll get these equations. The concentration of electrons n is equal to 2 into 2 pi mn kt by h square whole power 3 by 2 into e power minus ec minus ef by kt. You know all the terms what are present here. Let me just go through it. Yeah, 2 pi are constants. Mn is what? Effective mass of the electron. K is the Boltzmann constant. Capital T is the absolute temperature. H is the Planck's constant. Ec is the what? Bottom of the conduction band. Ec, or I can say edge of the conduction band. Ef is the Fermi level. Again K and T, you know. Okay, yes. Now what this nc here is, okay, what this nc, so nc is equal to 2 times of 2 pi mn kt divided by h square whole power 3 by 2. This is called as, okay, please the name, whatever name we are giving, you need to be very careful, you must understand it. Okay, so this is nothing but called as effective density of states, effective density of states at the edge of the conduction band. Yeah, this is important, very important. Okay, at the edge of the conduction band. Okay, hope I am clear. And what could be the units for this? Yes, what are the units? Represented with per centimeter cube. It is what are the units of nc? Per centimeter cube. Okay, here the important point, I am talking effective, it is not the total. Why it is at the edge of the conduction band? Why it is edge of the conduction band? We have applied the parabolic approximation here, and we know very clearly that n of e that we have obtained is only at the edge of the conduction band by using parabolic approximation. Yes, hope I am clear. Yes, okay, now, okay, mathematically whatever the equation that we got, it's fine. Okay, now try to understand what each term is going to represent physically. Okay, please concentrate. What we got, n is equal to, it is nc into e power minus ec minus ef divided by kt. This is what we got. Okay, now let us try to understand each and every term what it is going to represent here. Okay, please concentrate. Yeah, what is this n? It is nothing but number of electrons. Otherwise, can I say number of occupied states? Am I clear? Number of electrons is nothing but what? Number of occupied states. Okay, so let me write that. It is number of occupied states. Okay, now what about nc? Just now we have given, it is the effective density of states at the edge of the conduction band. Can I say number of available states? Number of available states. Am I correct? Yes. Okay, please, whatever you are calculating, it is at the edge of the conduction band. This is default. Okay, so I'm not explicitly mentioning that point. Okay, so number of occupied states at the edge of the conduction band, actually I'm not mentioning that. Okay, Hope I am clear. See, I know how many number of available states are present. How to get, you need to just multiply with the probability. Am I correct? I'll repeat this point. I know how many number of available states are present. Now what I want to calculate is how many are occupied. You just multiply with the probability. So this is nothing but actually probability, but with the Boltzmann approximation. FB, but where? At the edge of the conduction band, EC comma T. Okay, we'll see how we can get this actually. Let me write the equation. Okay, I'll write here. Let me write here itself. F of EC comma T, okay, is equal to what? It is 1 divided by 1 plus e power EC minus EF divided by KT. Okay, so in place of E, I am putting EC because where I am calculating at the edge of the conduction band, no, so I am putting EC. Okay, now you can very clearly see the conduction band. If you consider, you can say EC minus EF is going to be greater than or equal to 3 times of KT. You can consider very easily because where this Fermi energy level is going to be located at the middle, we have considered, no. Okay, so we can very clearly see this condition is going to be satisfied. If this condition is satisfied, we can very clearly see e power EC minus EF divided by KT is much greater than 1. Then what is FB of EC comma T? So 1 you can neglect here. It is e power minus EC minus EF divided by KT, and that is what we have written there. Hope I am clear. Yes, I'll repeat. See, this is how many number of states are available. What you want to find out of which how many are occupied. You just multiply with the probability, and that is what we have done here. Yes, clear? Yes. Now let us go for concentration of holes. Okay. Yeah. Before going to that, we need to have effective band picture. Actually, we'll try to draw that. Okay. So here, how we have represented. I'm talking about only the conduction band here. Let us consider. Okay. So this is EC and this is EV. Okay. And N of E, how we have represented something like this. This is N of E. Am I correct? So this is called as actual band picture. What we have drawn now is actual band picture. Okay. Now instead of total N of E, now what I am going to do is, okay, so this is EC now and this is EV. Now N of E is replaced with NC now. Okay, so it's a delta function here. This is NC per centimeter cube, because if you see the equation here, what we have written, N is equal to NC is present. Now what is this NC we have taken? Effective density of states at the edge of the conduction band. So simply these many number of states I am going to have at the edge of the conduction band. It is a delta function. Area under this will give NC. Okay, so this is nothing but what? Delta function. Area under this will give what? NC. What are the units? Per centimeter cube. So this is called as effective band picture. Effective band picture. Okay, hope I am clear. Yes. In the similar way, later on we are going to define similar type of thing for the valence band also. Okay, 1 minute. Okay, so this is about what? Concentration of electrons in the conduction band. Okay, now let us find out concentration of holes in the valence band. Okay, concentration of holes in the valence band. Okay. Yeah, the procedure is going to be the similar to what we have done for the concentration of electrons in the conduction band. Okay, but we'll see what is the difference. Okay. Now again, let us consider this is electron energy. Okay, this is the top of the conduction band, bottom of the conduction band. This is top of the valence band. Okay, and this is bottom of the valence band. Okay, so this is ET, EC, this is EV, this is EV. Anyhow, our interest is going to be where now? In the valence band. So this is the using the first principle. What is that? Allowed states we have represented. Yeah, then what we need to represent? Density of states. So we know this, okay, like parabolic approximation you can do, and this represents what? This is nothing but N of E. Okay. Now, what we are going to find out here? Concentration of holes. Nothing but what? Hole is nothing but the absence of the electron, or I can say unoccupied state in the valence band. Am I correct? Okay. Now, yeah, similar type of procedure we are going to follow as what we have done. Okay, but what could be the difference? You must understand here. Okay. So again, we consider a differential energy level here. Okay. So how many number of states are going to be present within that differential element? It is N of E dE. Okay. So since I have considered the differential interval, okay, so let me represent the differential element here. Let us take somewhere here. Okay. 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 So let us represent. This is the energy interval that I'm going to consider. What is this? dE. Fine. Now, the total number of states is Ne, but I am considering the differential element dE. Okay. So since I have considered the differential element, the number of holes that are going to be present are also differential in nature. So dP equal to, yeah. So what could be the term that I need to write now? If you remember this, what we have written here, F of E comma T, because this is the probability of finding an electron. But here what I must write? It should be 1 minus F of E comma T. Please try to understand this, because I am calculating the concentration of holes in the valence band. What is a hole? It is nothing but the unoccupied state in the valence band. So if F of E comma T is the probability of an occupied state, what is the probability of an occupied state? We have done the numerical problem also. It is 1 minus, and that is what I am writing here. Yes. Okay. Now, I should know what is the shape of this, 1 minus F of E comma T, that I can put it into this equation, okay, into this graph. And then the similar procedure that what we have followed earlier, we can do the same. Okay. So let me get first what is 1 minus F of E comma T, and then we'll go for the further discussion. Okay. So let us take, this is the probability. Okay. And this is the energy. Okay. This is the energy. Now this is 0. Let us take, this is 0.5. This is 1. Okay. Hope I'm clear. Okay. And let us take somewhere here I have EF. Okay. It's nothing but the EF. So let me represent first F of E comma T. How? Yes. What is F of E comma T? You get something like this. Listen. We know it is symmetrical with respect to EF. Okay. So I can draw. This is nothing but what? This is nothing but F of E comma T. Now what is 1 minus f of e comma t? You can very clearly get from this, like this I am going to get 1 minus f of e. Okay, so what is this one? It is 1 minus f of e comma t, this shape. Okay, so this is nothing but what? Fermi energy ef. So you can very clearly see the important conclusion that we can make out of this. Okay, both f of e comma t and 1 minus f of e comma t are or symmetrical with respect to what? Ef. So this is the important conclusion that you can make. Okay, is it fine? Okay, now you just overlap this shape, okay, into this one. Okay, whatever the 1 minus f of e comma t is there, you can write here. Again, Fermi energy level will be located somewhere at the middle. Okay, for time being you assume, later we'll see that. Okay, now let me draw that 1 minus f of e comma t here. Okay, something like this you are going to get. So this is nothing but what? 1 minus f of e comma t. Am I clear? Okay, the same procedure what we have done in the concentration of electrons in the conduction band. I am doing the same, but what is the difference that you must understand here? This term 1 minus f of e comma t you must write here. Okay, and this is what we can. Now what is dp here? Dp is nothing but you have to multiply these three, no, where you can represent that point here. Yes, nothing but this portion. Am I correct? This represents what? Hope I am clear. Yes. Okay, now if dp is equal to what we got? N of e, okay, that is differential amount of holes, is 1 minus f of e comma t. Okay, then how to get the total is you need to integrate within the valence band. What is that? eb to eb n of e d into 1 minus f of e comma t. Sorry, hope I am clear. Yes. Okay, so in the similar way, the graphs that we have represented, you can understand from this also. This is actually what? Take eb, this is eb, okay, and this is n of e, I can say. Okay, and 1 minus, if you represent, we got something like this. Yes, sir. Sorry, n of e is not this, because we must draw from this. No, let me first write 1 minus f of, then we'll go. Okay, like this. This is 1 minus f of e comma t. What is n of e? We must draw from this. This is what n of e is going to. Am I correct? Now, if you consider this line, blue line, what this is going to give? What this line is? N of e into 1 minus f of e comma t. And if you get the area under this curve, you can get the concentration of holes. Am I correct? The similar type of thing we have represented even in the calculation of this electrons. Okay, so this is EB, this is EB. Okay, and what is n of e? Something like this, n of e. And what is 1 minus f of e comma t? You get something like this. Okay, so this is 1 minus f of e comma t. Here I am not completing the 1 minus f of e comma t. Okay, you can draw the shape also, but this is important for us. I am confining to that portion. Okay, so this is the border, and you calculate this area. So what this is going to give? Concentration of holes. Hope I am clear. Yes. Okay. So similar type of things what we have done for concentration of electrons, I am doing here also. So again here we need to make approximations. Okay. Again, our interest is not in the mathematical derivation or integration of this, but you must understand physically what they are going to represent. Okay. So try to understand this now. Now, the first approximation that we can make here, we can very clearly see. Okay. From this or even in this graph also you can see. Your 1 minus f of e comma t is becoming 0, okay, before your EB itself. Am I correct? 1 minus f of e comma t is becoming 0 here itself. EB is somewhere here. Now you locate EB here or here or here or here. Okay, it will not affect the value of 1 minus f of e comma t. So what we are going to do is we'll put this as minus infinity. This is the first approximation. In the previous case, okay, where we have kept it at infinity, because this is the reason. Okay, whether ET is present here or here or here or here doesn't matter, and that is the reason why we kept it at infinity. But here it is minus infinity. Hope I am clear. Okay. Then what is the second approximation? It is the approximation. What it is? Parabolic, because that is how we have represented your density of states now. So it is nothing but parabolic density of states function. Okay, approximation. Hope I am clear. So this is the second one. So what it is? What I can write this one as some constant A2, okay, into under root EV minus E. Okay. Now what is the third approximation? Boltzmann approximation we need to do. Third one is 1 minus FB of E comma T. 1 minus FB of E comma T. Boltzmann's approximation. Okay, so do these all the approximations and find out the expression. We are going to get P is equal to 2 into 2 pi MP KT divided by h square 3 by 2 into e power minus EF minus EV divided by KT. Okay, so you can very clearly see only the different term here is MN and MP, otherwise it is the same. Okay, so this we can write it as P equal to NV e power minus EF minus EV divided by KT. Okay, so these are the equations that we are going to get. This is nothing but what? Concentration of holes in the valence band. Okay, concentration of holes in the valence band. Is it fine? Okay. Now, what is this NV? We can write now. What is NV here? Let me write NV is equal to 2 times of 2 pi MPKT divided by h square whole power 3 by 2. It is called as effective. Again, please, again, the terms are the terminology that we are using, you must understand. Okay, so effective density of states. Effective density of states. Where? At the edge of the valence band. Okay, so this is important. Okay, I am not saying that it is the density of states. What it is? What it is? Effective density of states at the edge of the valence band here. Earlier it is conduction band, now it is valence band. Hope I am clear. Yes. Okay. Now again we'll try to understand this mathematical equation, whatever we have derived. Okay, physically what it is going to represent. Okay, Now let me write the equation first. What we got? P is equal to, we got it as NV e power minus EF, sorry, EF minus EV divided by KT. Am I correct? This is what we got. Now, what this P is going to represent? P is nothing but what? Concentration of holes. It is nothing but, can I say, number of unoccupied states? Am I correct? P is number of unoccupied states. Unoccupied. Am I correct? Now, what is this NV? Number of available states. Am I correct? Just now we have given what is the term NV is effective density of states at the edge of the valence band. So can I say number of available states? Number of available states. Yes. Then what this is going to represent? Yes. If you see the analysis that we have done in case of, for electrons, what we have given here, you can see what is this FB of EC comma T. I can say fraction of occupied states, nothing but, can I say, fraction of occupied states. Am I correct? Yes, fraction of occupied states. So that is the reason why we are multiplying with FB of EC comma T. Now here it is nothing but 1 minus FB of EC comma T. Nothing but, can I say, fraction of unoccupied states. Am I correct? So here these are number of available states. So usually all the states that are going to be present, the actual nature, if you consider all the energy levels which are present in the valence band, they are filled. Okay, but with the thermal energy or something, electrons are moving from valence band to conduction band. There are vacancies that are created, are unoccupied states, and that is the reason why you are calculating. Okay, so can I say this fraction of unoccupied states? Am I correct? Fraction of unoccupied states. Hope I am clear. Okay. Now you just calculate what is this 1 minus FB of EC comma T. Okay, we'll try to get it. Okay. So hope I am clear. Similarly, N, what we have taken, number of filled states or occupied states. We know total number of states that are available. Multiply with the probability, you will get it. So what is the probability of unoccupied state? 1 minus, and that is the reason why I am writing like this. Okay, hope I am clear. Okay, now let me calculate this. 1 minus FB of EC comma T, okay, is equal to what? 1 minus 1 divided by 1 plus e power, I'm sorry, it is not EC where we are calculating. I'm extremely sorry. It is EV, no? I'm sorry, please make a correction. You are calculating at where? At the edge of the valence band. It should be EV, not EC. I'm sorry. Okay. So it is e power what? EV minus EF divided by KT. Am I correct? Okay. Now this is equal to, so you can have the condition that, what is the condition to apply the Boltzmann's approximation? You can have EV minus EF, okay, less than or equal to minus 3 KT. You can see very clearly that is going to satisfy this, because EF will be at the middle of the energy gap. Below that I am having EV. So EF minus EV will become negative. So that condition is satisfied. If that is the case, okay, so what is the term that I can write now? This term, okay, e power EV minus EF, okay, divided by KT is much less than 1. Am I correct? Yes. And using the binomial expansion, you can write this. What is the binomial expansion? I have already explained this. 1 plus x whole power n is equal to 1 plus nx. So if that is the case, what I am going to get? What I am going to get? 1 minus, this is 1 minus, am I correct? Okay, you take this 1 plus e power ev minus ef by kt whole power minus 1, and that minus 1 I am putting here. So this 1 will go, that minus sign will go. What I am going to get? E power ev minus ef divided by kt. And that is what we have written there. Only the thing is, instead of ev minus ef, I am having minus of ef minus ev. Hope I am clear. Okay, so this is how we can understand physically what these things are going to represent, these mathematical equations. Please, whatever you are writing, okay, even single letter you are writing, literally you are writing, it is having some meaning. You must understand it. Okay, particularly when you are writing the mathematical equations, don't simply by heart them. Okay, you must understand why this term is present. So when you are deriving mathematical equations, not only here, later on in the devices also, please try to understand when you are doing some mathematical derivation, there are a lot of physical. If I am going from one step to the next step, you must understand the physical phenomena that is going to happen, so that you can have better understanding and you can easily answer the questions. Okay, and that is the reason why I am spending a lot of time here to explain very clearly. Okay, so please concentrate. Don't have second thought. Okay, whether these things are required or not. Yes, these are required. Okay, am I fine? Okay, now we'll go for the actual energy band diagram and the effective, that what we have represented in the will represent here also. Now this is actually what? EB, and this is EB, allowed states. Then you can have N of E, something like this. You got, this is N of E. Okay, so this is nothing but what? Actual band picture. What we have written now is, in the valence band I am concentrating. Okay, actual band picture. Now what could be the effective band picture? Yes, instead of N of E, what I can write now? Anyhow, here EB will be at infinity. No need to indicate. I think same thing here also. Where it is? Yeah, ET will be at infinity. Okay, no need to represent here. Fine. So EB at infinity. I'm not writing that. Okay. Now instead of complete N of E, what simply I can put NB. Again, it is a delta function. Area under this one will give what? NB. So this is NB per centimeter cube. So this is what? Effective band picture. So later we'll combine these two and we'll try to find out. Okay, effective band picture. That is, separately we have written in the conduction band and valence band. No, once we know the position of the Fermi level, okay, we'll put it into one diagram so that we can have convenient way of representation. Okay, hope I am clear. So this is about what? Concentration of holes where? In the valence band. Okay, see again, if you understand the concentration of electrons, how we have calculated, in the similar way we have calculated, but only the difference is what? This 1 minus that factor is different, that you must understand. Okay, hope I am clear. Now another very important one. Okay, very important one, which is called as the intrinsic concentration. Okay, so let me write the next topic that we are going to consider. What it is? Intrinsic carrier concentration, or simply concentration you can write. Okay, okay, represented with Ni. Okay, now what is the basic nature of an intrinsic semiconductor material? In an intrinsic semiconductor, please concentrate. In an intrinsic semiconductor, what? N is equal to P is equal to Ni. Yeah. Now some of you are asking doubts whether N and P is representing what? What N is going to represent? How many number of electrons are present in the conduction band? Nothing but the free electron. Okay. And P is what? How many number of holes are going to present in the valence band? And this must be same. Okay. That is why we are writing N equal to P. And Ni, okay, is some notation we are using, which is nothing but intrinsic concentration. Okay, so Ni is nothing but what? Either you can take it as how many number of electrons are present in the conduction band, or you can take how many number of holes are present in the valence band. Hope I am clear. Okay. Yes. There is a basic nature. See, you take any material, electrically it should be neutral. What is that law is called? Law of electrical neutrality. Yes or no? Law of electrical neutrality. What is the meaning of that? How many number of positive charges are there? Same number of negative charges must be present. Otherwise, it is not in the system. Okay. Hope I am clear. Yeah. Now we know the expressions for N and P now. Okay, so we can get into this, substitute into this N and P, and we can calculate some important relations here. Okay, some important relations. Okay, so try to concentrate. We'll see one by one. Okay, let us consider N is equal to. We have two expressions. No, we'll let N is equal to 2 times of 2 pi Mn kT divided by h square whole power 3 by 2 into e power minus ec minus ef divided by kT. And what is P? I can write what is P? 2 times of 2 pi mp kT divided by h square whole power 3 by 2 into e power minus what? Ef minus Ev divided by kT. Okay, so you can see very clearly in the constant terms, effective mass of electron is present. Why? It is you are calculating the regarding the electron. Effective mass of hole is present because of that hole you are calculating. Okay, now you multiply these two. Okay, multiply these two. So N into P is equal to, okay, so what it is, you can see very clearly. This is going to accept your Mn temperature. All other can be taken as the constants. Are you understanding? Except because temperature you can vary, no? So except the temperature, all other terms, if you multiply, they will have some numerical value, constants. So you will get some value here, some value. Okay, so let me take it as some constant. Okay, it's again representation. Okay, let us take it as a dash. Some a dash I am representing. All constants I am taking it as a dash into t cube. Am I correct? T cube, because t power 3 by 2 into t power 3 by 2 you are going to get. Okay, t cube into e power what I am going to get here. Yes, it is ec. Anyhow, this ef will get cancelled. I'll get ec minus ev by kT. So what is ec minus ev? Yes, if you see the energy band diagram, how you will represent? This is ec, this is ev. No, this is ec, this is ev. What is this? Nothing but the energy gap. Now in place of ec minus ev, simply I can write what? Energy gap. So this is nothing but some constant a dash t cube into e power minus eg by kT. Hope I am clear. Okay, now what is n into p? What is n into p? It's nothing but ni square. Can I say? So n into p is equal to ni square. Okay, so what is this law is called? What is this one? Yes, what is this one is called? Is the mass action law. Yes or no? It is called as what? Mass action law. Okay, so if that is the case, I can write Ni square is equal to some constant A dash into dq into e power minus eg by kt. Or from this, I can modify it as Ni is equal to, so you have to take under root. So under root of A dash, you will get some other constant, A into, okay, t power 3 by 2 into e power minus eg divided by 2 kt. Just I am taking the under root. Okay, am I clear? Yes, I'm just multiplying whatever the constants I have. I'm taking as one, one constant value, and what are the variables that are present, I'm putting it. Okay, and you must remember this. This is a very important one. You can even expect the problems. There are many times problems are given based on this mass action law. Okay, and many times we are going to use this. Okay, so what this mass action law is going to say? The product of negative charges and positive charges is going to be some constant. So n into p equal to ni square. Okay, anyhow ni square is constant, so p has to decrease. If p is increasing, n has to decrease. Okay, hope I am clear. And this is what we are going to getting finally. Okay, now if you consider this equation, okay, again based on this you can get the problems. Okay, please try to, they can give the intrinsic concentration at a particular temperature and ask you to find out at some other temperatures. Okay, so let me write this equation, and we can get some mathematical relation. What we got, Ni is equal to some constant A into t power 3 by 2 e power minus what, Eg by 2 kt. This is what we got. Okay, now suppose if I know what is the intrinsic carrier concentration at, ask you to find out what is the intrinsic concentration at some other temperature. Okay, so let us, I want to get Ni, okay, Ni at a particular temperature T. Okay, and I know what is at 300 Kelvin. Okay, yes sir. So you just put for numerator part you put T as the T, and for denominator what, 300. Okay, so if, and take the ratio. So A will get cancelled. What I can write here, T divided by 300 whole power 3 by 2 e power minus Eg by 2k into 1 by T minus 1 by 300. Yeah, please don't try to by heart this equation. Okay, try to understand how you are getting. Okay, see, this is, you take, this is Ni of T. Another equation you take, Ni of 300. In place of T you put just 300, take the ratio. This is what you are going to get. Okay, hope I am clear. This is how you can calculate. Okay, yeah, you can expect the problems based on this one, whatever we have given now. Okay, fine. Now let us consider again this equation, and further we can, in a different way we can interpret this one. Okay, so again I am considering what, consider Ni is equal to A into t power 3 by 2 e power minus Eg by 2 kt. So apply natural logarithm on both sides. Okay, so log of Ni is equal to, is log A plus 3 by 2 log of t minus Eg by 2k into 1 by t. Am I correct? And natural logarithm applying. Yeah, you can write ln also. Okay, it doesn't matter. Okay, log of Ni equal to log of A plus 3 by 2 log of t minus Eg by 2k into 1 by t. Okay, now let us plot. Okay, I'm plotting a graph. I'm taking, the x-axis. Okay, is going to be 1 by t. Let me write neatly. Okay, I'm taking x-axis is what? 1 by t. And the y-axis is going to be the, ni in logarithmic scale, intrinsic concentration. Anyhow, this is going to be a constant. No, log of A is going to be constant. This will not change anyhow. Okay. And what about this? This variation is very small. This variation is very small. Yes or no? Because see, absolute value, if you take it into the logarithmic function, the variation is going to be very small. Okay, you know that. That's why you are representing in the, if you consider the amplifier, response that you are going to consider, where you are going to plot, not in the normal graph sheets. No, the reason is this one. Okay, okay, that you are compressing it actually. Okay, so even though t is larger, logarithmic of t you take, it's going to be very small. That's why this also I'm going to neglect. This anyhow is not changing. And if you get the graph for this, I'm going to get something like this. Okay, then what is the slope for this one? What is the slope for this one? Minus Eg by 2k. You know what is k? Boltzmann constant, no? So you can expect the problem. There are, 2 or 3 times there was a question theoretically as well as, mathematical also. They have given this graph and which parameter can be obtained from this. What semiconductor parameter you can obtain from this? You can very clearly see energy gap can be obtained from this graph. Yes or no? Eg can be obtained. Okay. So from this graph, you can obtain Eg. Eg can be obtained or calculated. If you know the slope, you can calculate. So please, okay. And you can expect the numerical problem based on this. Okay. They can give, slope and ask you to find out the energy gap. Okay. Hope I am clear. Okay. So this is how you can interpret what are the mathematical equations we have. Okay. Now we have, I think we have done with one mathematical equation. No, we'll take another. Yeah, we'll take the another. Okay. Now consider n is equal to what? Nc into e power minus ec minus ef divided by kt. And similarly, we'll take the p. What is p now? P is equal to nv e power minus ef minus ev divided by kt. Okay, now multiply the two. Multiply the two. So n into p is equal to nc nv e power minus ec. Sorry, ec minus ev. Ef will be get cancelled. Take the multiply. Okay, this is what we are going to get. Okay, so this is nothing but what again I can say nc nv e power minus eg by kt. Now what is n into p is ni square. Am I correct? So I can say ni square is equal to nc nv e power minus eg by kt. So from this what I can say, ni is root nc nv, okay, e power minus eg by 2 kt. So this is another way of representing your intrinsic concentration. Okay, so the previous one or this one, okay, both are going to be useful depending upon the condition. Okay, any way you can represent. Hope I am clear. Okay, yes, am I clear? So this is the what is about what? Intrinsic carrier concentration. Okay, so we know the what is the characteristic of the intrinsic semiconductor material, which n is equal to p, which is equal to ni, and from that, okay, either you can use this equation which we have derived, or in terms of NCNB, that is what we have considered. So you can expect the problems based on whatever the equations that we have derived. So please try to don't try to remember these equations. Okay, try to understand how you are getting them, so that you can apply for any type of problem or any type of question that is going to be present in your examination. Okay, don't try to by heart it. Okay, hope I am clear. Yes. Now let us consider the last topic in the intrinsic semiconductors, okay, which is again a very important one. Okay. So now we need to get where the Fermi energy is going to be located. Okay, so what we need to obtain now? Position of Fermi level in intrinsic, or simply Fermi level. Okay, Fermi level in an intrinsic semiconductor. Intrinsic semiconductor. Okay, hope I am clear. Now again, we know what is N and P, and what is the characteristic of intrinsic semiconductor. N is equal to P is equal to Ni. From that we can derive this. Okay, yeah. Simple mathematical rearrangement you do, you can get it. Okay, so let me write that first. For an intrinsic semiconductor, okay, we can say N is equal to P is equal to what? Ni. Yes. Now, what is N? What is N we got? It is Nc into e power minus Ec minus Ef divided by Kt. And what is P we got? Is Nv e power minus Ef minus Ev divided by Kt. Okay, now take N is equal to P. Yes sir. N is equal to, so it is Nc into e power minus Ec minus Ef divided by Kt is equal to Nv into e power minus Ef minus Ev divided by Kt. Okay, yeah. Please do some rearrangement. Find get from this what is Ef. Okay, so take this Nv to this side or Nc to this side and exponential to the other side. Okay, and apply the natural logarithm, rearrange the terms. Please make it fast. Do it. You just rearrange. Take Nc to Nv or Nv to exponential term to the one side, and then apply the natural logarithm on both sides. Get what is Ef. Please make it fast. Make it fast. Okay, so I'll write here. You will get Ef is equal to Ec plus Ev divided by 2 minus Kt by 2 ln of Nc by N. This is what you are going to get. Okay, or if you take Nv by Nc, then you can write it as plus here. That is the difference. Okay, hope I am clear. Or the same equation I can also write like this: Ef is equal to Ec plus Ev divided by 2 minus Kt ln of under root Nc by Nv. Anyway, you can write both will be the same. Okay, anyone in way you can represent this. Okay, hope I am clear. Yes. Now we know what is Nc and Nv. Okay, what is Nc actually? We got it is 2 times of 2 pi mn Kt divided by h square whole power 3 by 2. Am I correct? And what is Nv? We got Nv is equal to 2 times of 2 pi mp Kt divided by h square whole power 3 by 2. Okay. Now if you substitute into this equation, what I can write now? What I can write? Ef is equal to Ec plus Ev by 2 minus Kt by 2. Okay, you can see very clearly except Mn and Mp, all other terms will get cancelled. So Mn, sorry, logarithmic function is there, no? Kt by 2 ln of mn by mp whole power p by 2. Hope I'm clear. Yes. Yes. Now if mn is approximately equal to mp, okay, if mn is approximately equal to mp, that is the effective mass of electron and effective mass of hole, if we take it as same, what this term is going to be, this ratio is 1, logarithmic of 1 will become 0. So what I'm going to get finally, ef is equal to ec plus ev by 2. Okay, I can say approximately, not exactly equal, approximately. So it's nothing but what, eg by 2. Yes or no? Ec plus ev by 2 is nothing but what, half of the energy gap, no? Yes. Okay, so that is the reason why we are taking, it is present. Okay, I cannot say exactly at the middle of the energy gap or approximately, because what we have taken, mn is approximately equal to mp. Okay, so what I can say now, I'll write here itself, ef lies approximately at the middle of the energy gap, at the middle of the energy gap, for what, intrinsic semiconductor material. That is important. Okay, I'm not generalizing. Okay, it is present energy gap for what, intrinsic semiconductor, intrinsic semiconductor. Okay, or in general, this is the equation that what we have derived. In specific to the, we are applying that to the intrinsic semiconductor material, then you can say mn is equal to approximately mp. If they are not same, then there will be a difference. Okay, but in our discussions, whenever you are going to consider the intrinsic semiconductor material, what we are going to take, it's going to be at the middle of the energy gap, middle of the energy gap. Hope I am clear. Yes. Okay, now this we have given what you call mathematically, or we have explained. Okay, but we can explain this even in terms of, you know, conceptually also we can understand it's going to be present, okay, at the middle of the energy gap. Okay, we'll see how it is going to be. Now before going to that, let us consider this equation. Okay, again we'll try to understand how it is going to vary with respect to temperature. Okay, this is also important. Consider what we got, ef is equal to, we got it as ec plus ev by 2 minus kt by 2 ln of nc by nv. Am I correct? Now my question is, suppose if I increase the temperature, what will happen? If I increase the temperature, okay, what will happen to the Fermi energy level, whether it's going to increase or decrease, or it will move upward or downward, that you must understand here. Okay, are you getting? If I increase the temperature, what will happen to the location of the Fermi level? Okay, now we can very clearly see here. Suppose anyhow this is going to be, not constant, but take it as constant. Okay, because it is energy gap also changes with temperature, let us keep it constant. Okay, now if you increase the temperature, what will happen? If you increase the temperature, what will happen? T is increasing here. Am I correct? Am I correct? T. And if you increase this, the subtracted value is going to increase. Means what? EF is going to decrease, or I can say EF moves downwards. Okay, please try to understand. EF is decreasing. Means what? Okay, so as T increases, this KT by 2 ln of NC by NV, okay, is going to increase. Okay, and this makes, okay, this makes your EF decrease. Let me write. here itself, right? This makes EF to decrease. Nothing but EF decrease means, can I say EF moves downwards? Okay, what it indicates? EF moves downward. Am I correct? EF decreases means what? EF moves downward. Okay. Now, please concentrate. There is a question from my side. You need to understand. Okay. I am asking the doubt now. Okay. Instead of you, I am asking the doubt. Now, NCNV. What are the NCNVs we have given here? You can very clearly see. Okay. So this MN, MP are there, no? MN, MP. Okay. So they are not the same. Okay. And if you consider that equation again, what I can say now, EF is equal to, in that, EC plus EV by 2 minus KT by 2 ln of MN by MP whole power 3 by 2, no? Now is MN is less than MP or MN greater than MP? Earlier, if you remember, we have given MN is less than MP. If that is the case, this becomes what? This factor MN by MP becomes less than 1. Logarithmic minus, and minus into minus will become plus. Then EF should increase, nothing but it should move upward. Again, I'll ask my doubt. NC, NV I am putting and take the ratio. This is what we got. Okay. Now we know that MN is less than MP. Yes, MN is less than MP. If that is the case, this is the less than 1 factor. MN by MP is less than 1. Taking the logarithmic function of that will give the negative value, and already there is a minus sign. So total effect will be plus. Nothing but as you increase the temperature, EF is going to move upward or increasing. Okay. So now how you can justify? Whatever I have explained here, because of that I am getting EF decreases and moving downwards. But now according to this, it's going to increase, nothing but moving up. So how you can justify? So here, this is what you must understand very carefully. Okay, this MN, MP, what we are defining, okay, they are going to be relative terms. They are not the absolute terms. Okay, so there are, earlier what we have discussed is the effective mass with respect to conductivity. But now what you are talking here, these are the effective density of states. So with respect to that, we must understand what is the effective mass. Okay, so let me write that. Please concentrate. So if you say conductivity, okay, conductivity, effective mass. Okay, so in that case, Mn will be less than MP. That's going to be correct. Mn is less than MP. And if you take the actual mass, Mn by M naught, okay, so this value is going to be 0.26, and this is MP by M naught is going to be 0.38. So this is for silicon I am talking, okay, for the silicon material. Okay, and if you go for what we are considering here is effective density of states. Okay, so can I say density of states effective mass? Density of states effective mass. Okay, it is not the conductivity, it is what? Density of states. Then Mn will be greater than MP. Okay, and again for silicon I will give the value. No need to remember these values, but you must understand, if I take density of states with respect effective mass with respect to density of states, Mn is greater than MP. With respect to conductivity, if you take, Mn is less than MP. That is my intention. Okay, for different materials these are going to be different. Okay, so this will give 1.18, and MP by M naught, I think it is 0.81. 0.81. Okay, and if you take the these values and all, and if you substitute again for silicon, okay, you will get NC value, okay, is going to be 2.8 into 10 power 19 per centimeter cube, and NB value will be 1 into 10 power 19 per centimeter cube. So whatever I have explained now, that is going to be valid now, because I'm getting Mn greater than Mp, no? So this is Mn greater than Mp, which is greater than 1. Logarithmic function of greater than 1 value is positive, and whatever we have explained is going to be correct. Okay, please, you need to understand the effective mass that we are going to talk, okay, is not going to be an absolute term, it is a relative term, that you must understand. Okay, so if I talk with respect to conductivity, is less than Mp, but with respect to density of states, what it is, Mn is greater than Mp. Okay, so if you increase the temperature, what will happen to the Fermi energy level? It will move downward in the intrinsic semiconductor, that what we have considered. Okay, hope I am clear. Yes. So this is about what? So we have seen mathematically what this Fermi level is going to be. Okay, conceptually also we can understand where the Fermi energy can be able to locate it. Okay, yeah. Now we'll go for the quick doubts. Okay, for another 10 to 15 minutes, and then we'll go for break. Okay. Yeah, Lakshmi Kant.
Sir, good morning, sir.
Very good morning, please.
Sir, I have a small doubt on the 1 minus f of e comma t graph, sir.
1 minus f of e comma
E comma t.
Please.
So can you please draw?
I have already drawn, no?
Yes, sir.
Drawn. Try to get it, man. It's a
Yes, sir. Yes, sir. That graph.
That's what. What is your doubt?
Sir, if I erase the 1 minus f of e comma t is representing the states which are not occupied by the electrons.
Obviously.
If I erase the upper part of the EF, upper part of, above the upper part, above the part.
This one, huh?
Yes, sir. If I erase that part.
Why you want to erase?
I wanted to know one conclusion, sir. That the remaining f 1 minus f of e comma t graph represents the states which are occupied by the holes. Is it correct, sir?
Correct only, no, man. If I say electron is not present, that we are calling it as hole. Nothing but the unoccupied state.
Yes, sir. But in the conduction band there will be no holes, no, sir. In the conduction,
yeah, I said very clearly there is no meaning of talking about the holes in the conduction band.
So I have to erase the above part. It represents.
No, not required. Why you want to erase? I don't know. My question is, why you want to erase? What is the problem with that?
I want to show the graph of the holes occupation, sir.
Where?
In the valence.
That's what. No, that's what I have already done.
Okay, sir. Okay, sir.
Okay.
Okay, sir. Okay, sir.
Fine.
Thank you, sir.
Yeah, Guduru 1450. Yeah, please go ahead.
Good morning, sir.
Very good morning.
Sir, page number 67F, sir.
7F.
67F, sir. 67. Sir, if the Fermi level moves down, means the occupied states in valence band will be decreases, sir.
How? It will increase, no?
Occupied states.
Yes, occupied states.
Electron occupied states. Sir.
Where?
Valence band.
Obviously decreases. That's what you will call it as the hole, no? And the other way, hole concentration is going to increase.
Okay, sir. And page number 63F. Sir, you told that if P increases, means N will decrease in mass action law.
Yes.
Sir, but N equal to P equal to N Ni, sir.
N equal to P is equal to. Ah,
Ni.
yes, yes, yes.
But according to law of action, no, if P increases, will N will decrease, sir.
Where P will increase, where N will increase. It can it happen in intrinsic semiconductor?
No, sir.
That's going to be applicable for where extrinsic semiconductor.
Extrinsic semiconductor.
Mm. But as a whole, when you take N into P, it should be Ni square.
Okay, sir.
Okay.
Thank you, sir.
Yeah, Ash.
Hello, sir.
Yeah,
Can you
please.
hear me?
Yes, yes. Go ahead.
Sir, in intrinsic carrier concentration Ni, we have taken EC minus EV as EG.
EC minus.
EC minus EV as EG.
I'm not getting
Energy gap.
EC minus EV. What
As
is that?
energy gap.
Yes, obviously.
Sir, and in Fermi level, we have taken EC plus EV as EG.
No. Yeah. EC plus EV, you calculate what you are going to get. EC plus EV by 2, it is going to be what?
Sir, it's going to be middle of the bands.
That is different. Middle of the energy gap is different, EG by 2 is different.
Okay, okay.
Are you getting?
Okay, sir.
Okay?
Okay, sir.
Fine. You can unmute, okay? Soumya, please go ahead. Soumya? Indrajit?
Hello, sir.
Yeah, please.
Sir, I have doubt on yesterday's class, sir. Sir, you
Yeah.
have drawn that Fermi energy level graph with respect to function at y-axis, no, sir? Sorry, y-axis.
F of E comma T, I have taken x-axis.
And
E minus EF, I have
energy of
taken
an electron is at x-axis, no, sir. Sir,
no, y-axis.
yesterday I have checked.
Energy
Sir,
on, please, 1 second. Energy on y-axis, F of E comma T on x-axis.
sir, we can interchange the graph also, no, sir?
Yeah, you
Then
can
also the results will be same,
Yeah,
no?
you can interchange. See,
And
if you change the axis, what will happen? Nothing is going to happen, no? Parameters, if you change, then graph is going to change.
okay, sir. Sir, now in this page, intrinsic carrier concentration, you have said that N equal to P equal to Ni is Ni, no, sir. Then how you can multiply with the same
Means?
to get Ni square? No, sir.
Is N into P equal to Ni square or not?
Yes, sir.
What is the problem? See, I have not given N into P equal to Ni square. It is defined as the mass action law. It is a characteristic of the material. It is a characteristic of the material, okay?
I didn't get its significance, sir.
You will get it in when you are discussing about the extrinsic semiconductor material.
Okay, sir. Okay. Thank you, sir. Thanks a lot. Sir. Okay.
Shubham. Shubham, please go ahead.
Hello.
Yes.
Sir, I have a small doubt in yesterday's class that graph of that energy band.
Tell me the page number.
I don't remember the page number actually. You have drawn the
See,
metal.
are you there? Yesterday discussion, are you there?
I was there, but
Then why you didn't ask yesterday? Okay. Go ahead with your doubt. Don't waste time. Go ahead with your doubt.
When we expand, that means interatomic distance is decreasing. That time energy gap is increasing, right?
Energy gap is not increasing. Where it is increasing? Are you there at the beginning of the today's class?
Yeah, I was there.
I have explained already around 10 to 15 minutes. Only this I have explained.
Yeah. So what I want to say is, after the metal, that there will be a small energy gap, and after that it will be increasing, right?
Yes.
Then that part will be semiconductor, where the energy gap is small, and whenever it will be increasing, it will be insulator, right? After that, black.
That's what I'm telling you. See, 1 second, please hold on. energy gap for an insulator is how much? Around 6 electron volts. Huh?
6 electron.
So in that also, you need to decide the interatomic distance. So in that case, the interatomic distance is in such a way that the energy gap is going to be larger value.
Okay.
Is it okay?
Right. Okay.
Yeah.
Thank you, sir.
Okay. Yeah, Venkat Ganesh. Venkat Ganesh.
Hello, sir. Good morning, sir.
Good morning.
Sir, I have doubt in.
Please go ahead.
I have doubt in concentration of holes in valence band.
Hmm.
Sir, why should you take E? Why should you take EB as infinity, sir? Integration.
Have you listened to the class what I have explained?
Yes, sir.
Yeah. Why I have taken see the where your 1 minus f of e comma t is become. Can you see this?
Yes, sir.
Here itself 1 minus f of e comma t became 0. No.
Sir, I can't understand your voice, sir.
1 minus f of e comma t,
Hmm.
where it became 0. Can you see here itself it became 0? No.
Oh, okay, sir.
Now whether you place EB here or here or here or here at infinity, will it affect your 1 minus f of e comma t value?
No, sir.
That's why I kept it at minus infinity.
Okay, sir. Thank you, sir.
Yeah, Rohit. Rohit.
Good morning, sir.
Yeah, good morning. I think your voice is not that much louder.
Now I'm audible, sir.
Go ahead.
Sir, I have a doubt on 57F.
57F.
67.
67. Yeah, I think you need to be somewhat louder. Yeah, please go ahead.
Sir, I didn't understand relative mass concept and how it will affect those two equations.
See, please, those who are asking the doubt, you need to be isolate from the other disturbances. See, behind you there are so many people who are talking. I'm not getting your exact one. Move from that side or ask them to move. Yeah, please go ahead.
Sir, what you said about relative mass, I didn't understand, and how relative mass concept will affect those two equations.
It is effective mass. How it will affect? See, what is M and MP? M and MP are going to be the effective masses, no?
Yes.
Okay. Can you see in the mathematical equation M and MP are present?
Yes.
Now, will they affect your EF or not?
Yes.
That's what. If Mn is less than MP, what is this factor? Mn by MP is going to be less than 1?
Yes.
Logarithmic of that function will become what?
Negative.
Negative. Already minus sign is there.
Yes.
So overall it will become plus.
Yes.
Now you increase the temperature. According to that, what will be the EF? Will it
Will move
or,
upward.
But Mn actual scenario is, I am talking with respect to density of states, Mn is greater than MP.
Yes.
Then what will happen to EF if you increase the temperature?
It will move downwards.
That's what I have explained, no?
Okay.
Got it?
Okay, sir.
Yeah.
Yes, sir.
So we need to consider density of states effective mass, not the conductive effective mass, because we are talking about density of states now. So the
Yes.
second one we need to consider for discussing about the Fermi energy level. Got it?
Yes, sir.
Okay.
Thank you, sir.
Yeah. Ayyappa, please. Ayyappa, please. Nazir. Nazir.
Hello, sir.
Yeah, please.
Sir, in page number 59F.
59F.
Sir, how EC minus EF is greater than 3 kT?
See what I said, Fermi level is located where we have taken at the middle of the energy gap, no?
Yes.
EC, whatever we are going to consider the energy levels in the conduction band. Okay.
Yes.
What is the lowest band?
Sorry.
What is the lowest possible energy in the conduction band?
EB. EC.
EC. So whatever energy levels that you are going to consider, definitely they will be above EC.
Yes.
Okay. And now EF, wherever we are going to get, okay, so it is going to be at the middle.
Yes.
Okay, so definitely it is going to be. Later we are going to take the numerical value also, once we still have not completed the Fermi energy level location. Theoretically I have explained. You take the silicon as an example. What is the energy gap at a room temperature? 1.1 electron volts.
Yes.
Am I correct?
Yes.
3 kT means what? 3 kT. kT is 0.026 into 3. You compare EC minus EF and 3 kT.
Yes, it will.
Okay?
Yeah.
Yeah.
Thank you.
Okay. Gautam? Gautam. Yeah, please, those who got doubts are get clarified, please unmute your voice. Yeah, please, Gautam, go ahead.
I have a general doubt, sir.
Okay.
Can you go to page 60F, the next one, sir?
60F.
Sir, here actually what is P, sir? We are calculating the number of holes present, right, sir?
Yeah, obviously. P is the number of holes.
Are those holes total number of holes in this semiconductor material?
Total number of holes?
In this semiconductor material or only in the valence?
In the same, I am getting a lot of disturbance from you.
No, sir, it's not from me. The remaining students, Saurav and someone else, their mic is on.
Okay, 1 second, I will close them. Please, those who doubts are get clarified, please unmute your voice, please. I'm not having it. Okay, go ahead. It is of the semiconductor or?
Semiconductor or only of the valency band, sir?
The valency band is for what? Valence band correspond to me or you or semiconductor?
Semiconductor only.
Obviously, it is a total, no? Semiconductor. As a whole, you are considering, no?
No, sir. My doubt, why I got the doubt is when we were integrating, we took the limits from EV to minus infinity.
Minus infinity to EV, not EV to minus infinity.
Yeah, sorry, sir. Minus infinity to EV. But seeing this Fermi-Dirac curve, having curve even above EF.
Above EF, okay, it will be.
And even we have some number of states which are starting from EC, density of states curve. In EC. So those both, when they are multiplied, there are holes there, no, sir.
How you can multiply? Where holes are there?
In the conduction band.
See, I have mentioned very clearly, please be careful. There is no meaning of talking about holes in the conduction band. I very clearly mentioned. What is the meaning of holes in the conduction band? Tell me, because it's initially, what is the basic nature? There are no holes, no electrons at all in the conduction band. Means you can call all are going to be holes, no? But what is the concept of hole? What is the concept of hole we have discussed?
I mean, absence of electrons.
Where?
In the valency band.
Then why you are talking about vacancy in the conduction band?
Yes, sir. I totally get what we discussed back, but when we multiply,
are you getting now what I am talking?
Yeah, yes, sir. Yes, sir. I get that. When we multiplied these two curves to find number of holes in the conduction band, I was of the opinion that
no, in the valence band. Again, you need to correct yourself.
Yeah,
calculating hole concentration in valence band.
Yes, sir. So I thought that we are even having some available density of states in the conduction band, right? N of E. So I thought that N of E multiplied with 1 minus F of E will show that there are holes.
If you remember, when I start discussing about concentration of electrons and holes, I repeatedly 2 or 3 times I mentioned there is no talking about concentration of electrons in the valence band, because already there are, but they are not free electrons.
Okay.
And we are not supposed to talk about the holes in the conduction band. It is meaningless.
Yes, sir, I get that now. Sir, and actually, what does this intrinsic carrier concentration Ni physically signify?
How many number of electrons and holes are going to be present? That is what it is going to signify. Later, if you move for X-NIC semiconductor material, you will get better clarity.
Okay, but I heard this statement long back saying that Ni in an intrinsic semiconductor defines the minimum amount of current that will flow through a semiconductor. Is it right, sir?
Obviously, no. Because that many number of charge carriers are there, and for intrinsic, if once your electron and holes are, you see, these are the different way of interpreting the things. The same information you can interpret in a different way. That's a different thing. You can call it.
Can we say that the available number of electrons and holes can never be less than this Ni?
Obviously, no.
Yes,
obviously.
Thank you, sir.
Yeah, Nani, please go ahead. Nani?
Hello, sir.
Yeah, please. Yes.
67F.
Which one?
67F.
I'm not getting clearly. There is disturbance. Hello?
Hello, sir.
Yes. Hello?
Can you hear me, sir?
Yes. Now it's okay. Fine. Go ahead.
I have a doubt in 67F.
Yeah, please.
Sir, I couldn't get the difference between conductivity effective mass and density of states effective mass.
What do you want to understand here? See,
mass.
Have you understood a conductivity effective mass? Already we have discussed this.
Yes, sir.
Yeah. Now, effective mass is an absolute term or relative term?
It's in relative term.
Relative, correct? So, with respect to what parameter you are considering, depending upon that, it is going to change.
Yes, sir.
When you are talking with respect to conductivity, this is what we got. But now, when you go for density of states, what you must understand is, see, suppose you move some electrons from valence band to conduction band.
Yes, sir.
Okay. So first, what will happen? In the valence band, topmost is the EV. No, from that electrons will move, and EC is the lowest energy possible in the conduction band.
Okay.
So they will be occupied first, and later on it will go to the higher energy levels. Now you try to understand, if you want to move electrons further from valence band to conduction band, how much effort you ought to put, and that you relate to your effective masses, that you can understand now.
Okay.
Got it?
Yes.
Yeah, Ashwatthama. Yeah, please, those who doubts are get clarified, please unmute your voice first. Ashwatthama. Saurabh.
Hello.
Yes.
Hello, sir. You can hear me?
Yes. Go ahead, please.
Sir, I have a doubt in page 62F.
Fine.
Sir, the FB, how you, sir, binomial expansion, how you did it, sir?
Are you there in the yesterday's class?
Yes, sir.
Yeah, we have done the same thing. The same repetition I have done here. Same yesterday, what the Boltzmann approximation, have you seen?
Yes, sir.
Have you written that?
Yes, sir.
Yeah, go through that Boltzmann approximation for the second condition. Same thing I have done here.
Sir, in
Boltzmann approximation, second condition we have done, the same thing I have done here. You just put on paper, okay? Try to spend some time.
Okay, sir.
You will get it. Is there any other doubt?
Sir, in n equals to nc e to the power EC minus EF by KT for n, and P for EF minus EV, sir. Why both are different, sir?
It's a mathematical derivation, man. You need to do the derivation. YE means where the location of your EC and EV are going to be present, and where EF is going to be present. Maybe 1 second. Maybe after this, doubt session, once we get back after the break, we'll discuss, where the Fermi level. Okay, now we have decided where the Fermi energy level is going to be. Yes, where the Fermi energy level is going to be. Now this location will decide how many number of electrons are going to be present and how many number of holes are going to be present actually. Okay, and if you see the mathematical derivation that we have taken, where it is, yeah, in this one you can see very clearly. Okay, 1 minus fp of ev comma t, this is the expression we got, correct?
Yes, sir.
Can you able to see?
Yes, sir.
That is what I put that in a different way, that's all. Mathematically it's okay, but physically what it is going to represent, we'll see. You can understand, no? You can try to suppose if ef minus ev, okay, is increasing, what will happen? Try to understand. Are you getting my point?
Yes, sir.
ef minus ev is decreasing, what will happen to p? Try to understand in that way, then you can able to understand why it is like that. Okay, once we start discussing about the extrinsic semiconductor, you will get more clarity, because in n-type semiconductor material, what are the majority carriers?
Holes.
N-type semiconductor, what are the majority carriers?
Electrons, sir.
Electrons. Okay, so this Fermi level will move closer to the conduction band. In p-type semiconductor, holes are going to be majority carriers, it will move closer to the valence band.
Okay, sir.
That you can understand there. Okay,
Okay.
fine. Okay, we'll take 15 minutes break. Okay, so it is 11:25, we'll meet at 11:40. Okay, welcome back, students. Now, mathematical representation that we have given for the Fermi energy level, we'll try to understand in the theoretical way also where it can able to present. Okay, so what we are going to discuss now is location of Fermi energy level EF by simple reasoning. We'll see by simple reasoning. Okay, so here what I'm going to do is I'll assume the location of the Fermi level. Okay, first I'll assume, okay, and then I'll check whether my assumption is going to be correct or not. Are you understanding? So again I'm repeating, I'm going to assume the position of the Fermi level, and then okay, I'll check whether it is correct or not. Okay, in that way we are going to check it now. Okay, now let us consider the first one that I'm going to consider or I'm going to assume is, okay, so let us take it is in the conduction band, for example. Okay, so where I'm considering EF in conduction band, CB I'm writing. Okay, this is my assumption. Okay, so let me write that and then we'll check. Okay, assume EF is in conduction band. Okay, so I'm assume EF is in, okay, where? Conduction band. And now we'll try to check whether this is correct or not. Okay, so let me write, this is EC, okay, and this is EV. So this is EC, this is EV. Okay, then I'm assuming where the Fermi energy level is located in the conduction band. Let us put here. Okay, this is EF. Okay, and here another important point, I'm taking T is equal to 0 Kelvin. This is also important. Okay, the temperature what I'm considering here at absolute 0. Am I correct? Okay, absolute 0. Now we know very clearly, please concentrate. We know very clearly that at absolute 0, all the energy levels that are present below the Fermi energy level are filled states, and all the energy levels which are present above the Fermi energy level, they are empty. That is the physical significance of EF we have given. Now if that is the case, we can clearly see that these states must be filled states. Am I correct? According to the physical significance of the Fermi level, then we can very clearly see these are going to be what? Filled states. Okay, but is it correct? Okay, according to our assumption of the Fermi level, these states should be filled, but we know that at absolute 0, the valence band is completely filled, the conduction band is completely empty. So this is not possible. Okay, this is not possible. This is not possible. Am I correct? Yes, this is not possible because according to our assumption of Fermi energy level, I am getting the filled states, but at absolute 0, intrinsic semiconductor is going to behave like an insulator. There are no electrons that are going to present in the conduction band. Hope I am clear. Yes. Now I am taking the second assumption here now. Okay. Now again at T equal to 0 Kelvin only I am considering. Okay. Now assume EF is in valence band. Where I am considering it is in valence band. Okay. Now let me represent the energy band diagram first. Let us take, this is EC, this is EV. So this is EC, this is EV. Now I am assuming that it is present in the valence band. Let me indicate here, this is EF. Okay, this is EF. Okay. Now again consider the physical significance of Fermi energy level at absolute 0. Okay, any energy level that is present below the Fermi energy level, it is filled, above it is empty. Yes, So if that is the case, these states, whatever the shaded line, shaded area that I'm representing with the green lines, this should represent what? Empty states. This should represent empty states. Okay, am I correct? But is it correct physically? We know at absolute zero in an intrinsic semiconductor material, the valence band is completely filled, conduction band is completely empty. So this is also not possible. This is also not possible. Am I correct? Okay, so both the conditions what we have assumed is not going to possible physically. Okay, now let us consider now third condition or third assumption that we are going to take. Okay, now I am taking T greater than 0 Kelvin. Okay, assume, okay, either you assume close to the conduction band or close to the valence band. It's your wish. Okay, are you understanding? What we are doing is, what is the possibility? Please concentrate. What is the possibility? Either it can be in the valence band or it can be in the valence band. Now in the middle, in the energy gap. Yes or no? In the energy gap. These are the three possibilities. We have checked, it is not going to be possible. Okay, in the conduction band it cannot be present. In the valence band also it cannot be present. What is the next option? Within the energy gap. Now within the energy gap, let us assume either it is close to conduction band or close to valence band and check it. So here I am assuming that EF, okay, assume EF is closer to EC. Closer to what? EC. Is it fine? And we'll check whether this is correct or not. Okay. Now let us take the energy band diagram now. Okay. Okay. Represent the EC, EV here. This is EC. Okay, let me write here EC. Where is EV? Let me take, this is EV. Okay, hope I'm clear. Now we are representing the Fermi energy is going to be closer to conduction band. Let us take, this is here, closer to conduction band. Am I correct? Okay. Now let us indicate density of states here. This is N of E. Okay, and this is N of E. This is in the valence band. This is in the conduction band. And now represent F of E comma T and 1 minus F of E comma T. What they are going to represent? From that we can get how many number of electrons are present and how many number of holes are going to be present. Okay. And what is the important point here? We have already mentioned both F of E comma T and 1 minus F of E comma T are going to be symmetrical with respect to the Fermi energy level EF. Okay, so this point is important. Hope I am clear. Okay, both F of E comma T as well as 1 minus F of E comma T are going to be symmetrical with respect to the Fermi energy level. Now depending upon that we need to draw F of E comma T and also 1 minus F of E comma T. Okay, let me draw that. Okay, so this is nothing but what? F of E comma, yes. And what about 1 minus F of E comma T? It should be symmetrical, no? So we'll get somewhere here. Okay, so this is what? 1 minus F of E comma T. Now what is the concentrations here? If you take this area, okay, what I'm going to get? Concentration of electrons. And this area, this small area is going to represent what? Concentration of holes. Okay, and what you are going to get here according to this, N is going to be greater than P. But is this correct? This is also wrong, not possible. Why? Because it is intrinsic semiconductor material, N must be equal to P. N must be equal to P. So in the similar way, you take it as an exercise and work out. Okay, take the fourth case. Again, it is T greater than 0 Kelvin. You consider. Okay, assume. Okay, EF closer to EV, closer to EV. That is, you place this EF closer to EV. Try to draw the similar type of diagrams. What condition you are going to get now? P will be greater than N, and this is also not possible. Yes, this is also not possible. Try to draw this diagram, fourth diagram. Okay, so it is not possible. So what you can conclude finally? What you can conclude? Okay, so by considering the discussion that we made now, I can say EF is located, okay, approximately at the middle of the energy gap. Middle of the energy gap. So please, whatever mathematically that we have represented, you must understand it conceptually also, and that is what we can able to finally conclude it. Okay, hope I am clear. Yes, yes. Okay, now we'll try to understand the Boltzmann approximation. No, okay, we have given the Boltzmann approximation. Okay, we'll try to understand whether it is applicable or not. Okay, try to understand this. Now consider Boltzmann approximation. Consider the Boltzmann approximation. So what it is valid for two conditions we have taken. What is that? Okay, so it is valid, okay, for E minus EF greater than or equal to 3 kT, or E minus EF is less than or equal to minus 3 kT. Yes, okay. Now let us take silicon material. Okay, I'm discussing with silicon, and it is a room temperature. What is the energy gap at room temperature for silicon? It is 1.1 electron volt. Okay, yes. Now what is Eg by 2 from this? What is Eg by 2? It is 0.55 electron volts. 55 electron volts. Now calculate EC minus EF. Where the EF is going to be? EF is at the middle of the energy gap. Middle of the energy gap. Okay, so if that is the case, what is EC minus EF? Is going to be equal to 0.55 electron volts, because EC minus EF is nothing but Eg by 2, which is 0.55 electron volts. Okay, and we know KT is equal to how much? 0.026 electron volts. Calculate 3 times of that, 3 kT. Okay, yes, it is 0.078 electron volts. So 0.078 electron volts. Yes, so you consider, what is the lowest possible energy in the conduction band. See, this is the energy band. If you consider, this is EC, this is EV. So EC is the lowest possible energy. Okay, your conduction band is from EC to infinity. That is what we have taken. Valence band is EV minus infinity to EV. Okay, from minus infinity. Okay, so any energy level that you are going to consider now in the conduction band, okay, if it is satisfied for EC minus EF, it is satisfied for almost all. Okay, so if that is the case, we can very clearly see from this, whatever we have taken, we can see EC minus EF is going to be greater than or equal to 3 times, not equal to also, it's going to be greater than itself, you can say. You can very clearly see. Okay, so in the similar way, you try to analyze, you are going to get EV minus EF is going to be less than minus 3 kT. Okay, so what we can conclude here is, for all the practical purposes, okay, the Boltzmann approximation can be applied for the semiconductor materials. The reason is this one. Am I clear? Okay, so I can write a statement here. Okay, EC minus EF in many semiconductors, okay, in many semiconductors, okay, will always be what? Greater than 3 times of K. Okay, will always be greater than or more than 3 kT. Okay, 3 kT at any temperature that we are going to consider, at any temperature. So in the similar way, if you consider, what is that? EV minus EF is going to be less than minus 3 kT. Okay, so we can say Boltzmann approximation is going to be valid. Okay, so similarly, EV minus EF is less than minus 3 kT. So Boltzmann approximation is valid. Please try to understand this point. Okay, what is the reason? We have given the location of the Fermi level. From that we are deciding this. Okay, hope I am clear. Yes. Okay, so this is about what? Fermi energy level. Okay, now we'll try to give the actual energy band diagram or energy band picture and the effective band picture. Okay, so try to understand, because we know where the Fermi energy level is going to be located. Now we can draw it. Okay, okay, so let me draw that. So first I'll take the actual band picture. From that we'll try to draw. Okay, so this is the y-axis represents what? Energy here. Okay, yes. Now what is EC? Let me locate here. This is EC. Let me take this is EV, and you can represent this one is what? ET. Let me write ET, and this is what? EB. Is it fine? Okay. Now what is N of E here? We have represented something like this, N of E here, and this one. Okay, this is N of E, this is N of E. Now we know where the Fermi energy is located. Let me indicate that also. At the middle, approximately at the middle. So this is nothing but what? EF. Am I correct? Yes. Okay. Now can you represent 1 minus f of e comma t now? Yes or no? How it is going to be? Sorry, f of e comma t. With respect to EF, you can write 1 minus also. Okay, let me represent. Okay, so something like this you are going to get. Okay, so what is this one? F of E comma T. Yeah, I'm not completing. If you want to complete, you can also complete. There is no issue with that. Okay, we'll get the other part also. Hope I am clear. So this is nothing but what? The actual band picture, you can see. Actual band picture. Okay, so now we'll try to draw the effective. Okay, so again, what is this? Electron energy. Okay, now this is nothing but what? I can say EC, EV, This is EF. Am I correct? EF. Okay. So this EF, you may represent like EI here. What is EI here? Intrinsic Fermi level. Again, these notations may change from textbook to textbook. Please keep it in mind. Okay. So here I am taking Fermi energy level for intrinsic is what? EI. Okay. Now to draw the effective band picture, what we are NF with at EC, we have replaced it with what? With NC. Okay, it's a delta function. Yes or no? So NC per centimeter cube. And similarly at EV, N of E has been replaced with what? NV, effective density of states at the edge of the valence band, like this. Okay. And what about F of E comma T now? It's going to be the Boltzmann approximation to the F of E comma T with a little variation. Okay, with little variation. You may not see exactly what's the difference. Okay, now this is nothing but what? FB of E comma T. So instead of Fermi Dirac, Boltzmann we are representing here. Okay, so this is nothing but what? Effective band picture. But it is effective band picture. Okay, hope I am clear. Okay, so we know what is the actual band picture, effective band picture in the conduction band, valence band. I'm combining. Also, we know where the Fermi energy is located now. I'm including into the energy band. Okay, hope I am clear. Yes. Okay. Now we'll try to take up some numerical examples so that we can understand whatever we have discussed in a better way. Okay, so try to. So here, consider this problem. Okay, calculate the probability that a quantum state in the conduction band. Okay, so they have given E is equal to this one. It is sorry, EC plus KT by 2 is on, and calculate the thermal equilibrium electron concentration at room temperature. Okay, assume the Fermi energy is 0.25 electron volts below the conduction band. Value of NC is given. Okay, and KT is also given. Yeah, here you can see they have very clearly mentioned what is the KT value. Suppose if they have not mentioned, what is the value that you can take? 0.026 electron volts. If they have mentioned, please take it. Okay, hope I am clear. Yes. Now how to find out? What is the first thing that we need to find out? Probability. What is that? We can take the Fermi Dirac distribution function. Okay, so F of E comma T is equal to what? 1 divided by 1 plus e power E minus EF divided by. Is it clear? Okay, so now they have very clearly mentioned what is E. Just put it into this. So this is equal to 1 divided by 1 plus e power. In place of E, what I can write? It is EC plus KT by 2 minus EF divided by KT. Okay, so can I say now F of E comma T is equal to 1 divided by 1 plus e power. Okay, can I say it EC minus EF plus KT by 2? Sir, no. Okay, and divided by KT. Divided by KT. Am I correct? Okay, so this is nothing but what? 1 divided by 1 plus e power. EC minus EF is given. You can see very clearly here. Assume the Fermi energy is 0.25 electron volts below the conduction band. So what is this value? This value is nothing but, okay, so I can put it here. So how much it is? 0.25 plus 0.0259. Okay, let me take divided by 2. Okay, and whole divided by 0.0259. Okay, so we calculate this value. calculate this value. Okay, or the same problem, because we can apply the Boltzmann approximation also. You can calculate, there will be a slight difference. Okay, you can do it in another way also, because I can apply the Boltzmann approximation. No, yeah, you can calculate in this way also. There is no issue with it. Okay, we are going to simplify more. Okay, so if I say FP of E comma T, Boltzmann approximation, if I consider, I can neglect 1 compared to this. No, from that also you can calculate. Okay, it's going to be more simple than whatever we are substituting now. Okay, almost you are going to get the similar type of values, because you are adding only +1 in the denominator. Okay, yeah, you can calculate in any way. Okay, so this is minus EC minus EF plus KT by 2 whole divided by KT. Hope I am clear. From this, you just take the Boltzmann approximation, or you substitute from this also, you can calculate. There is no issue with that. Okay, yes. So this value I am giving, you check it later, is going to be equal to, okay, let me give that value, 3.9 into 10 power 5. 3.9 into 10 power 5. Okay, there will be because there is one +1 in the denominator, there will be little change. Okay, if you use the actual one. Okay, so try to compare the two values. Okay, now what is the other parameter that we need to obtain? Yes, calculate the probabilities over, okay, occupied by an electron. Calculate the thermal equilibrium electron concentration. So because I am taking equilibrium, okay, you can put it as N0. So N represents what? Concentration of electrons, and this suffix indicates it is under equilibrium. So what is the formula? So again, it is the notation. Okay, so N0 is, we know it is Nc e power minus Ec minus Ef divided by Kt. So we know Nc is given in the problem, 2.8 into 10 power 19 into e power minus, what is Ec minus Ef? 0.25 divided by Kt is 0.0259. Okay, so you calculate this value, you will get it as 1.8 into 10 power 15 per centimeter cube. Okay, is it clear? Yes, hope I am clear with what I have done. Okay, so there are two things that you need to find out here. One is the probability, another one is equilibrium electron concentration. Okay, so this is how you can calculate. Okay, yeah, yes, can I go to the next one? Yes, now calculate the thermal equilibrium hole concentration in silicon at T is equal to 400 Kelvin. Now it is not 200. Okay, assume that the Fermi energy is 0.27 electron volts above the valence band energy, and NV is given. Okay, and T is given